Alright, so the first thing we have to prove is the a squared plus b squared is greater or equal to 2ab, and we already know. If we do a minus b all squared, we know that that has to be greater than 0, and that expands to be that, and therefore a squared plus b squared is greater or equal to 2ab. So that's that first one. We're good with that. We do that all the time. So let's try the second hence. So we're going to use that for hence. Prove that blah 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 equals blah blah blah. Okay, so you can see it's got a squared and b squared and c squared. So I'm going to try all the different combinations. So not only do I have a squared plus b squared greater or equal to 2ab, I would say similarly b squared and c squared would be greater than 2bc, and a squared and c squared would be greater than 2ac. So if I add those all together, I've got two lots of a squared, b squareds and c squared. So two lots of each of a squared, b squared and c squared being greater or equal to two lots of ab, bc and ac. And of course then we would say now we're going to divide both sides by 2 and we would get our answer. So we've done that before as well. So let's have a look at c then. Oops. So given that, now we're given something, which is an equal sign, and we're going to prove an inequality. So we could start with where's C? There we go. We could start with our B, because it's got the, if we put it all on one side, we do have the a squared plus b squared plus c squared minus ab, bc and ac being greater or equal to 0, and this one we know has to be greater or equal to 0 because it's the product of two positive terms because of part B. So if I just rearrange, alright, so let's say from part B, yeah, I don't maybe know if I'd go this way, but anyway, we'll try. So from part B, if I just put everything on one side, we know that a squared plus b squared plus c squared minus ab minus bc minus ca has to be greater or equal to 0. And that's this bit here, yes? So we can say, well, therefore we know that a plus b plus c and a squared plus b squared plus c squared minus ab minus bc minus ca, that has to also be greater or equal to 0, since how do we know that a plus b plus c is positive? Oh, here we go. A, b and c are all positive. So we've got a, b and c. Oops, oh, I've written a since a, b and c are all positive, and so what I really could say it's the product of two positive terms. So perhaps if I say from b that and and we are given, why did it do that on me? And we're and given a, b and c are positive, a plus b plus c has to be positive. Therefore, this has to be greater or equal to 0, since it's the product of two positive factors. Something like that will do. Alright, or two positive terms. Alright, therefore, if we look at this side, which is equal to those things, we know it's got to be greater or equal to 0. So we've got a cubed, b cubed, c cubed, minus 3abc. So that has to be greater or equal to 0, since it's equal to this. And if we just rearrange that, we get what we want. So just putting that 3 on the other side, 3abc, we then get this inequality here. So then D just says if x, y, and z are positive, show that x plus y plus z is greater or equal to 3 x, y, z to the power of a third. So really you can see that all we're doing is making x equal, so we'd say, you know, it's this same equation, we're just subbing in. So we're letting a cubed equal x. So in effect we're letting a equal x to the third. Yeah, so if you need to figure it out. B would equal y to the third, and C equal z to the third. If we do that, we get x to the 1/3 cubed, which is just x, y to the 1/3 cubed, which is just y, and z to the 1/3 cubed, which is just z, is greater or equal to 3 lots of x to the 1/3, y to the 1/3, and z to the 1/3. So you can see here this just becomes x plus y plus z is greater or equal to 3. Let's put x, y, and z together, and they're all to the power of a third, which is what we wanted here. So sometimes you just have to sub in to the inequality you've already proved.